Welcome to the Explainer. So, when you zoom way in on Google Maps or you're checking out the satellite view on your phone and you just marvel at how stunningly clear your neighborhood looks from space? I mean, you can see houses, cars, even individual trees. It feels like absolute magic. But actually, it's a brilliant, completely invisible mathematical process. Today, we're unpacking the fascinating world of image pansharpening.
Okay, let's dive right into this by asking a really logical question, one that pretty much everyone wonders about at some point. Why can't a billion-dollar satellite just take high-resolution color photos right out of the gate? We live in the modern era. We've all got smartphones in our pockets with incredible high-megapixel cameras. So surely a giant satellite can do the exact same thing, right? Well, it turns out it's not about the budget, and it's definitely not outdated technology. It is strictly a physics problem. Satellites orbiting hundreds of kilometers above our heads have to make a really tough choice. They have to compromise between spatial sharpness and spectral color. So, here's our roadmap for this explainer. We're going to cover the resolution trade-off, what pan-sharpening is, how image fusion actually works, compare some different techniques, look at the spectral integrity catch, and finally, talk about how to choose the right method.
All right, Section 1, the resolution trade-off.
To really understand the solution here, we have to understand the physical limitations of collecting photons of light from outer space. Think of satellite sensors like giant buckets trying to catch photons. A panchromatic sensor is like one massive bucket that collects all visible light at once. Because it's so big, it gathers a massive amount of energy, which means engineers can make the physical pixels really, really small. The result? You get a beautifully sharp, high spatial resolution image. But because it just throws all that light into one bucket, the image is entirely in black and white. On the flip side, you have multispectral sensors. These are like smaller buckets that split the incoming light by specific colors, like red, green, blue, and near-infrared. Since each of those color buckets only collects a tiny fraction of the total light, the pixels literally have to be larger just to get a clean signal without a bunch of digital noise. The result there, fantastic color, but a blurry, lower spatial resolution image.
And there's a magic ratio to keep in mind here, 4:1. This isn't just some random number, it's practically an industry standard baked right into satellite hardware. Take the WorldView 3 satellite, for instance. Its panchromatic black and white band captures stunning detail at 0.31 meters. But its color, multispectral bands, those capture at 1.24 meters. That is exactly 4 times coarser. So every single time a satellite passes over, it's simultaneously capturing a razor-sharp black and white image and a blurry color image. So, how do we fix that discrepancy?
Moving on to Section 2. What is pan-sharpening? This is exactly where the math swoops in to save the day. By definition, pan-sharpening is an image fusion technique. It takes that high-resolution panchromatic image and merges it directly with the lower-resolution multispectral imagery. Put simply, we're taking the sharp spatial details, the crisp edges, the really fine textures from the black and white image, and we are injecting them straight into the blurry color image. By fusing them together, we trick the final output into giving us the absolute best of both worlds, high spatial resolution and high spectral resolution. Okay, Section 3, how image fusion works. So how is this magic trick actually pulled off by the software? Let's walk through the standard component substitution method. It's basically a highly choreographed dance with 6 precise steps. First, we upsample the color bands, digitally stretching out that blurry image so it matches the size of the high-res panchromatic band. Second, we perfectly align these bands so absolutely nothing is distorted. Third, we mathematically transform the color bands into an alternate color space, which separates the intensity or the brightness from the actual color information. Fourth, we match those intensity levels. Fifth, and honestly this is the most crucial part, we perform component substitution. We literally swap out the blurry intensity component and entirely replace it with our razor-sharp panchromatic data. And finally, step 6, we reverse the transform back into our normal red-green-blue color space. The final result is a stunning, sharp, full-color image. Which brings us to Section 4, comparing pan-sharpening techniques. Now, the specific math used in that substitution step, that can vary wildly. Think of these different algorithms like a toolkit, where every tool has a specific superpower and, a specific kryptonite. We're going to look at 3 major ones today: IHS, Principal Component Analysis, and High-Pass Filter. IHS relies on a color space shift. It's super fast, but it can sometimes distort colors. PCA uses a statistical transform, while HPF focuses on spatial filtering. Let's break these down to see what they're actually doing to the satellite data. First up, we have intensity, hue, saturation, or IHS. This method takes our standard red, green, blue image and converts it into 3 distinct channels: intensity, hue,
and saturation. It takes that low-res intensity component, completely throws it out, drops in the high-res panchromatic image, and then converts the whole thing back to RGB. It is absolutely fantastic for visual sharpness. Your image is going to look incredibly crisp, but it kind of acts as kryptonite for spectral accuracy. Because you're artificially swapping brightness values around, the exact shades of color might be mathematically distorted from what was originally captured.
Next up is principal component analysis, or PCA. This is a super powerful statistical approach. Instead of just looking at color spaces, PCA transforms the multispectral image into what we call principal components, based on data variance. In remote sensing, we generally assume that the first principal component holds all the spatial information of the image. So PCA just integrates the high-res panchromatic data right into that first component before converting the data back. It's a mathematically robust way to handle really complex datasets. Then we have the high-pass filter, or HPF. This one approaches things a little differently. It uses spatial filtering to extract only the high-frequency spatial detail from the panchromatic band. We're talking about the edges, the sharp lines, the outlines of buildings and roads. It takes those sharp edges and essentially overlays that high-frequency detail onto each upsampled color band. HPF is widely loved in the GIS community because it strikes a really great balance. You get a visually sharper image while still preserving a reasonable amount of the original spectral integrity of the colors. Now, beyond those three, there are a couple of other heavy hitters you're definitely going to encounter in GIS software. There's the Brovie transformation, which multiplies pixels by a ratio of panchromatic to multispectral intensities. It's computationally really simple and gives great visual contrast. But the real star of the show in modern commercial processing is Gram-Schmidt. It uses a concept called vector orthogonalization. And look, don't let the math jargon scare you. All you really need to know is that Gram-Schmidt is widely considered the absolute best general-purpose algorithm out there. It simulates a low-res pan band, decorrelates the vectors, and ultimately balances incredible sharpness with true-to-life color fidelity better than almost anything else. It really is the commercial gold standard.
All right, Section 5, the spectral integrity catch.
However, all of this mathematical magic comes with a pretty big warning label. The fundamental rule of remote sensing data is that you just cannot get something for nothing. Pansharpening fundamentally changes pixel values. Yes, the visuals improve dramatically to the human eye, but the original spectral signatures, the exact digital numbers recorded by the satellite reflecting off the Earth, are altered. If you're a scientist trying to calculate quantitative metrics, like say the NDVI to check crop health, Pansharpening will absolutely wreck your calculations. You're injecting artificial math into raw scientific data, and that's a huge no-no.
Finally, Section 6, choosing the right method. So, keeping that major catch in mind, how do you actually know when to use this? Well, here is your definitive guide. Use Pansharpening when your main goal is visual interpretation. If you're doing urban mapping, tracing the footprints of individual buildings, trying to spot vehicles, assessing storm damage, or you just need to create a really beautiful map to present to stakeholders, you absolutely want that 4x resolution boost. It makes everything so much easier to see. But you have to skip Pansharpening if you're doing quantitative spectral analysis, calculating indices like NDVI, or running automated machine learning land cover classifications based on raw spectral signatures. In those specific cases, you've got to stick with the raw, blurry color data because the underlying math is pure. I want you to remember this quote. It's practically the golden rule of geospatial imagery. Don't sacrifice spectral accuracy for pixels you don't need. It perfectly captures the delicate, incredibly important balance we've been talking about today between stunning visual clarity and rigorous data integrity. Well, we've covered a ton of ground in this explainer, from the physical limits of optical space sensors all the way to the brilliant algorithms that help us completely overcome them. So I'll leave you with this final thought. Next time you pull out your phone, open up a map app, and zoom in on your neighborhood from space, will you spot the hidden math, making that image so brilliantly clear? Thanks for joining me on this explainer, and keep exploring.